Okay, hello everybody. Today I'm going to be explaining chromosomal abnormalities, what exactly are they, the two main causes of them, and specific examples that are most common to see. Now, when it comes to chromosomal abnormalities, we can link chromosomal abnormalities to either two causes. We can either link it to a numerical cause, so the problem is with the number of the chromosome, or we can link it to the structure of the chromosome. So there's a problem in the chromosome, problem in the gene, but it's structure. Now let's start by covering the numerical problems or the numerical mutations that we can see. So in the first thing that we can look at, it's polyploidy. Now in the case of polyploidy, the idea is there is a completely extra set of genomes. So a normal human being will have 23 pairs of chromosomes, or what we know as 46 chromosomes. So there's 23 pairs of 46 chromosomes. In polyploidy, there's a completely extra set. So a complete extra set of the entire genome. It can either be triploidy, so there is 3N, so that is 69 chromosome instead of the 46. So it's essentially 23 times 3. And usually this is a result of dispermy. So there are two sperms fertilizing one egg. Now, to keep in mind, in general, polyploidy, the zygote that does form will, for the most part, result in abortion. If it doesn't result in abortion, then we will usually see, most of the time, we'll see basically death by the first month, and we will not actually see a proper fetus with a triploidy or a tetraploidy, or in general, polyploidy. So triploidy is when there are 69 chromosomes or 3N. When it comes to tetraploidy, you have basically double the 46 chromosomes, or 4N, so 4 times the 23 chromosomes. So there are 92 chromosomes in the case of tetraploidy. So as we said, triploidy is the case, or it's when two sperms will fertilize one egg. In tetraploidy, usually the cause is failure of cytokinesis to occur properly. So what does that mean? Basically, a zygote will form normally. It will have 46 chromosomes, and then cleavage will happen, and it needs to reach a point where we can label it as a two-cell stage. And in the two-cell stage, the chromosomes will duplicate, and they would go through cytokinesis, in which each cell will divide, or the cell will divide into two cells, and this results in two separate cells that are 2N, 2N. So this is the ideal situation. Now, when cytokinesis doesn't happen, the cytoplasm will not divide, and so all of these 92 chromosomes, which were supposed to be divided into two separate cells to have 46 and 46, they will all go into one cell and result in 4N. Again, polyploidy, both of them usually will not survive. They'll usually result in abortion or death by the first month, like in the case of triploidy. Now, the other case of the numerical abnormality, it's aneuploidy. In aneuploidy, the problem is with a specific chromosome. So we know we have 23 pairs of chromosomes, and out of these 23 pairs, 22 of them is autosomal, and one of them is the sex chromosome. So it's either XX in females or XY in males. So this is the case that what we see in these 23 chromosomes. The problem with aneuploidy, or what results in aneuploidy, is you do not have the normal pairs of chromosomes. You can have an extra chromosome or a less chromosome. So there's a problem in the specific chromosome. This is usually a result of non-disjunction. Put in simple words, non-disjunction, it's basically the failure of chromosomes to separate properly. If we're looking at the meiotic division, a normal meiotic division, homologous chromosomes will pair up, so a maternal and a paternal chromosome will come and pair up together. In meiosis 1, they're supposed to divide. So these two will go here, and these two will go here, and they have two cells. And then these chromosomes, now we have them, the sister chromatids of them will split up, and we result in these haploid gametes, 4 haploid gametes, in a normal meiotic division. So in the first meiosis, the homologous chromosomes will separate, and in meiosis 2, the sister chromatids are going to separate. Non-disjunction can happen in either or. They can happen in meiosis 1 or in meiosis 2. In the case of meiosis 1, it's a bit more severe because it is from the beginning, and all 4 gametes will be impacted. All of them will have an abnormal number of chromosomes. In meiosis 2, only 2 of them will have an abnormal number. So in meiosis 1, what happens is these homologous chromosomes one of the homologous chromosomes found in the cells will not separate properly. And the entire 3 chromosomes, instead of, as we said in this example, 2 go to each cell, one cell will have 3, and the other will have 1. And so later on, meiosis 2 will occur normally, and the result is this. So 2 cells or 2 gametes will have an extra chromosome, or n plus 1, and the other 2 will have a deficient or less, because the problem was from the beginning, was from the first cell. So this is in meiosis 1. In meiosis 2, meiosis 1 will occur normally, so we'll have normal division of homologous chromosomes, but then the sister chromosomes will not divide properly in one of the cells. So this cell will divide normally, and you'll have 2 chromosomes, like in the case of here, in the normal meiotic division. But in the other case, this chromosome, both the sister chromatids will go to one cell. And so one cell will have an extra number of chromosomes, and one will have less. And then a sperm will come and fertilize an egg, this could be in the maternal or the paternal side, and the fertilization will occur, and we'll have 2n. But we still have minus or plus, so we still have an extra chromosome or a less chromosome. Now, this plus 1 or minus 1, there are specific terms for them. So there is monosomy and there is trisomy. Monosomy is when we have 2n minus 1. So 2n, it's the normal 46 chromosomes. Minus 1, that means we have 45 chromosomes in the case of monosomy. On the other hand, trisomy, or 2n plus 1, this is when you have one of the chromosomes, instead of being a pair, they're triple, so there's 3 chromosomes. And this results in, instead of having 46 chromosomes, we have 47 chromosomes. So this is the difference between trisomy and monosomy, both of them falling under aneuploidy. So let's start by looking at the actual examples of trisomy. We'll look at 3 examples of the autosomal trisomies, and then we'll look at what can happen if aneuploidy happens in these sex chromosomes, or the last chromosomal pair. So let's start with Down syndrome. Down syndrome is pretty normal. Actually, before we start with Down syndrome, there is something worth mentioning. It's that basically chromosomal problems and chromosomal abnormalities usually will always result in a developmental delay, growth failure, and a congenital anomaly. It's something in your chromosomes, so it's something that will be present at birth when the baby is born. Down syndrome, it is pretty common. It's found in 1 in 600 people. If we're looking at the craniofacial or the face region and what are the changes that we can see in the face, usually there is brachycephaly, so that is lower than normal ratio of the skull's length to the skull's width. There is a flat occiput or back of head. There is upward slanting palpebral fissure. This is the palpebral fissure here in the picture. There is the protruding tongue. So you can see in this picture, the baby has a protruding tongue. There is the short-nosed breast nasal bridge, epicanthus. So this is a picture explaining or showing epicanthus, which is basically a condition where the folds of the skin stretches from the upper to the lower eyelids. There's other things. So there's like the small and low-set ears, as you can see from the picture here, and the neck as well. You can see it's webbed, where it's like almost linked. There's also intellectual disabilities, there's microcephaly, short stature, and there's also problems in their hands or changes in their hands. So there's brachydactyly or short fingers. Clinodactyly, basically the child has, one of the fingers are curved or they're deviated. There's single palmar crease, like in this picture. So there's no, in a normal hand there are multiple creases, but in the case of Down syndrome you'll have a single palmar crease. There's also a Standel gap, so there is a gap between the two toes, so the big toe and the toe near it, there's a larger gap. There's also health problems, so problems with the vision, there's hearing loss, cardiac problems like ventricular septal defects or atrial septal defects. There's also problem with the endocrine system, which can result in like infertility and hypothyroidism, and even leukemia can also happen in patients with Down syndrome. Now, when it comes to this syndrome, you can actually differentiate it based on the cause, based on the type. So usually, basically this is done through karyotyping, and you can look at the chromosomes, and then from these chromosomal study, you can see what is the cause of Down syndrome. The first cause that we have is non-disjunction 21. And non-disjunction 21 is like what I previously explained. It's basically when the chromosomes do not split properly. And 94% of patients with Down syndrome, usually this is the cause behind it. To put more numbers into this, usually most of the time the non-disjunction happens because there's a problem in the maternal meiosis 1, which causes this non-disjunction. On the other hand, we have Robertsonian translocation, which is usually about 3% of individuals that have Down syndrome have Robertsonian translocation. And with Robertsonian translocation, the patient appears to have Down syndrome features, but upon closer inspection to the karyotype, it shows that they have 46 chromosomes, not 47 chromosomes. And this is because we have something called acrocentric chromosomes. So a centromere is essentially the middle region of the chromosome that holds the sister chromatids together. And certain chromosomes will have this centromere located pretty low. So like if we put like this or even lower, and we call them acrocentric chromosomes. These acrocentric chromosomes are chromosomes 13, 14, 15, 21, and 22. And usually these chromosomes can attach to one another. And this can result in balanced or unbalanced translocation. And in the case of Robertsoni translocation, it's unbalanced. The patient has an extra chromosome, but it appears to be normal chromosomal type because it's linked to another chromosome. So we do have an extra 21. So there is 3 chromosomes of 21, but one of them is bound to chromosome 14 or chromosome 22. And this can be linked to the parents having a balanced translocation. So the mother or the father can appear to have normal chromosomal type, so normal appearance, but upon closer inspection, it will show that they have 45 chromosomes. And this is because there is a chromosome attached to another chromosome, but they are fine. But this increases the chance of the parents having an offspring or a child with Robertsoni translocation. The final type of Down syndrome is mosaic Down syndrome, and this is usually, it results in milder symptoms and milder phenotype compared to the other types of Down syndrome, and it is more rare. It's only in 2% of patients with Down syndrome. Usually, as you can see from this diagram here, the fertilized egg has 46 chromosomes, so it's normal number. But as the cells starting to divide through cleavage, a mutation will happen, and some of the cells will have 47, while others will have 46. So certain problems can occur in the division later on, and it can result in Down syndrome, but it is milder since not all the cells will have 47 chromosomes, only some of them. And this is mosaic Down syndrome. So that is the first type of trisomy that we see, Down syndrome. Again, it's the most common type. Now moving on, we have Edwards syndrome. Edwards syndrome is trisomy 18, so you have an extra copy of chromosome 18. And we also have trisomy 13 or Patau syndrome. Something worth mentioning for both of them is usually the fetus will not live up until the first year. Usually it is a very severe illness or severe abnormality, and usually the baby doesn't live. So you do have certain problems and certain changes. So you have one of the most prominent things with children with Edwards syndrome is hypertelorism. So there is a large distance in the eyes, microphthalmia, so the eyes are small, short neck, microcephaly, developmental delays, and there's also again a distinctive change in their hands. So they do have overlapping fingers, they have an absent thumb. You can also see, so the short hallux dorsiflect is what you can see in this picture. There's a single palmar crease, so again that's the same thing here in this picture in Down syndrome, and a rocker bottom feet, so you can see how their feet look a bit different. And again, usually it babies and fetus who have Edwards syndrome, usually they do not survive their first year. Patau syndrome is similar to that, but it is even more rare. And with Patau syndrome, usually you have, again, microphthalmia, but something different from Edwards syndrome is the hypotelorism. So their eyes are closer to one another. There's cleft lip, and palate. There is developmental delays and brain problems, and something distinguishable in Patau syndrome is the hollow prosencephaly, which is basically the brain is two spheres, two separate spheres. In Patau syndrome, the brain is pretty much one ball, so it's not separated into two spheres. You've got microcephaly, growth deficiencies, and scalp defects that you can see in this picture where the skin isn't properly covering the head. Now these are the 3 main autosomal problems that we have. Now if we look at the sex problems or the problems with the sex chromosomes, we can basically link it to either the abnormal ova or the abnormal sperm. So a normal ova is supposed to have an X. So an ova is supposed to have, or an ovum is supposed to have an X, whereas a sperm is supposed to have either an X or a Y. This is in a normal case, in a normal scenario. In an abnormal scenario, an ova can have XX, so 2 X's, or no chromosomes at all. And then it can be fertilized by a chromosome that carries Y, and so this results in X, X, Y, and this results in a syndrome called Klinefelter syndrome. Or it can be fertilized by a sperm that's carrying an X chromosome, and we have X, 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 which is triple X syndrome. On the other hand, if it's not carrying any genetic material and it's fertilized by sperm carrying Y, we have something called Y0, and this is usually an incompatible with life, and so there is no fetus to begin with. If it's fertilized by a sperm that's carrying an X and the egg isn't carrying any genetic material, it's going to be X0, and this is what we know as Turner syndrome. On the other hand, a sperm can be abnormal if it carries both X and Y or doesn't carry anything. If it carries both X and Y and then it's fertilized by an egg, obviously an egg can only hold X, it'll be XXY, which is the same situation here, same situation here, and we said that this is the case of Klinefelter syndrome. If it doesn't carry anything and it's fertilized by an egg, then we have X, and this is what we have here and here. Obviously, we can add a 0 here, and this is what we know as Turner syndrome. So now let's look at Turner syndrome and Klinefelter syndrome. So Turner syndrome is the first example that we will, and the only example of monosomy. So that's when you have only one chromosome and not a pair of chromosomes. Usually with both Turner and Klinefelter, there is no cognitive impairment. They have normal IQs or around the normal IQ. But a girl with monosomy X will have a short stature. She will have certain features like a broad chest, widely spaced nipples. She'll obviously have problems with the reproduction. So she is infertile. A girl with monosomy X or Turner syndrome is infertile. They can be given hormonal therapy to produce the secondary sex characteristics, but they're still infertile. There is coarctation of the aorta or narrowing of the aorta, hearing impairments, and something very distinctive of people or patients with Turner syndrome is the congenital lymphedema or the puffiness of the dorsum of the hands and the toes as well, the hands, fingers, and toes. So this is the case of Turner syndrome. Now, if we look at the other sex chromosomal abnormality, it's a trisomy, it's Klinefelter syndrome, but we cannot call it trisomy X or trisomy Y since you do have both X and Y. So with Klinefelter, it's X, X, Y. So you cannot really say it's trisomy X or trisomy Y since it's not all the same chromosome. Again, there is no significant change in IQ or cognition. Usually, a male with Klinefelter syndrome will have long limbs, tall and slim stature, hypogonadism, infertility, and gynecomastia, which is basically enlargement of the breasts. So this covers all of the chromosomal abnormalities if we're looking at the number aspect, the numerical aspect. And most of the examples or all of the examples that we covered were related to aneuploidy, and we also spoke about polyploidy, triploidy, and tetraploidy. Now, looking at the other aspect of chromosomal abnormalities, it's structural. And with structural, you can have deletion, you can have duplication, inversion, and translocation. Deletion, as the name suggests, there's a certain segment of the DNA or the gene that is deleted or taken out. Duplication is you duplicate a certain segment. There's an extra copy of a chromosomal segment. Inversion, it's basically you take a segment, so you can see here, so it was originally CBA and then it was changed to become BCA. So there's an inversion. Translocation is when you have two different chromosomes and their genetic material flips or moves around. This isn't really as severe or as bad since the genetic material is still there, it's just located on a different region. It's like the Robertsonian translocation where we have the chromosome, it's just attached to another chromosome. We have the genetic material in translocation, but it moved or it swapped places with another genetic material. Now, the main examples we'll cover are with deletion, and something to be mentioned with deletion is you can delete only a segment of a chromosome. It's not necessary to delete the entire chromosome. So the main syndrome we'll talk about is Shahd syndrome or the cat-like cry syndrome, where we have a deletion in chromosome 5, or going back a bit, a chromosome has a P arm and a Q arm. P arm is the short arm and Q arm is the long arm. When it comes to Shahd syndrome, the deletion occurs in chromosome 5, but the P arm or the short arm. Usually there are growth failures, developmental delays. Again, the most distinguishable feature of it, as the name suggests, is a cat-like cry. Cleft palate might be common, and in general, there is a round face, hypertolerism, so there is the distance in the eye, like the case that we spoke about here in Edwards syndrome, where we said that they have hypertolerism, and then Patau have hypotolerism, and then Shahd have hypertolerism. There's epicanthus, again, like Down syndrome, and so on. There's Williams syndrome, so there's a deletion of part of chromosome 7. So it's part of chromosome 7, the Q arm. The part of it that's being deleted is 11.23. DiGeorge syndrome, again, it's part of chromosome 22. And usually this results in immune problems. So it's missing part of the thymus, or the thymus is completely not there. This can result in problems with B cells and obviously T cell deficiencies and so on. Then finally we have Prader-Willi and Angelman syndrome, again a deletion in part of chromosome 15, the Q arm and so on. And this is actually an example of genomic imprinting. Put in simple words, genomic imprinting means the syndrome will change, or the syndrome will be different depending on what parent you're getting the genetic abnormality from. So in this case, if it's maternal, the syndrome will be called Angelman syndrome. And if the syndrome is taken from the paternal side, or the abnormality or the mutation is taken from the paternal side, it will be called Prader-Willi syndrome. And that is pretty much it for chromosomal abnormalities and the different types and the different diseases.